The wooden head frame is subjected to loading shown. Determine the force in members Ji, Jd, and Id. To solve this problem, we'll have to cut this member twice. First to find the value for Ji and Jd. Then we'll have to cut once again between Hi and Ed to find our force for member Id using method of joints. Okay. Before we even begin, let's find our angle here. We're going to call it angle theta. To find angle theta, we know that our top member GF is 4 and our bottommost is 8 meters or 8 feet wide. So therefore the difference is 4 feet. And to get the difference on one side, either on G or F, we have to divide it by 2, and we know that's because this structure is symmetrical. So that means each side has extension of 2 feet in members. Therefore, to find our angle theta, we have to tan it, and it's going to be 2 feet divided by 16 feet, and this should get us our angle theta, and this comes up to be 7.13 degrees. Now that we have our angle theta, we can proceed with our first cut, and we're going to draw its free body diagram just to visualize better. So we have joint G and F, and we can have joint I and T. We'll have our unknown force Ij with angle theta. We're going to have diagonal force for member JD. I'm going to name this angle beta. We'll still have to find it. And then we're going to have another vector, unknown vector, for member DC. And angle here is theta. Now before we proceed, let's find our angle beta as well. So our angle beta is simply going to be tan, and we know vertical distance between I and J is 4 feet, and we know that each side grows or extends by half feet with every level of this truss or head frame. Therefore, when we reach J, our left hand side has extended by 1.5 foot, and our initial length was 4 feet. So we know on the right hand side, the extension is going to be 1 feet, and on the right, the extension is going to be 1.5 feet. Therefore, adding 1.5 feet and 1 feet to get our length of the horizontal width is going to be 6.5 feet. Tan of 4 divided by 6.5 feet is 31.61 degrees. Now we can take a moment about the point J in order to find our force in member DC. we're going to have horizontal and vertical vectors of the force DC. Our vertical vector for force DC is going to be clockwise, and it's 1.5 plus 4 feet plus the one on the other side, so 6.5 feet away. And then it's also clockwise horizontally. It's going to be sine 7.5 or 7.13 degrees times force DC, and it's 4 feet away. Then our external reaction force of 30K is also clockwise, and it's 1.5 plus the 4 feet, so 5.5 feet away. And then we have our 25K also in clockwise direction, and it's 1.5 feet away from J. All equals to 0. Solving for force DC, we get our solution as 29.15K, and it's in negative. This means we assumed our vector direction in the wrong direction. Switching it over will give us the correct orientation and our answer in positive. And this also tells us that this member is in compression. Now we can sum the forces or take moment about the point D, and in doing so it will give us a solution for force in member IJ. So we're just going to have the vertical component of IJ, which is going to be cos 7.13 degrees times force IJ, and it's 6 feet away from joint D. Then we're going to have our external reaction forces. Our 25K is counterclockwise, and it's 5 feet away. Then we have counterclockwise 30K, and it's 1 feet away. All equals to 0. Solving for IJ, we get our solution as negative 26.03K. This means negative means we assumed our vector in the wrong direction. Switching it over will give us positive solution and also tells us that this member is in compression. Now we can find our JD by either summing the forces in X or Y direction. I'm going to do it in X because we have lesser amount of forces in the X direction. So we're going to have horizontal component of IG, which is sine 7.13 degrees times force IJ 26.03K. We're going to have horizontal component of force DC, which is also sine times 1.3 degrees times force DC, which is 29.15K. And then finally we have the horizontal component of force JD, which is going to be cos 31.61 degrees, all equals to 0. And we get a solution for JD as negative 0.455K. As you know, if we got our solution in negative, this means we assumed our vector in the wrong direction. Switching it over gives us a positive solution, and this also tells us that our member is in compression. Okay, now that we have found our required IJ and JD, we have to tackle our problem for ID. In this case, we're going to redraw our free body diagram for our new cut, and here we're going to have our force HI, external force ED, and then the other diagonal force of EI. We're going to have new angle beta, our angle theta is going to remain same. And to avoid confusion, I'm going to name our angle phi instead of the beta. Okay, so before we proceed, let's find our angle phi. So in this case, we're going to have tan of 4 feet as before, because our height doesn't change with the levels, but we're going to have e to I. So one side is going to, right hand side is going to increase by only 0.5 and the left hand side by 1 feet. Therefore, 1.5 feet increase in force, so it's going to be becoming 5.5 feet. And our angle comes up to be 36.03 degrees. So after phi, we're going to have to use the same methodology as we did before. So we're going to take our moment above the point I. So we're going to have horizontal and vertical component of force FED. And both of these are clockwise. And then we're going to have clockwise 25K and 30K. External reaction forces are all equals to 0. Solving for ED, we get our solution as negative 29.39K. This means our vector direction in wrong direction. Switching it over, we know this angle or this member is in tension. Pardon me, compression. Now we can, like before, take moment about the point E. We're going to have just the vertical component of force HI. It's 5.5 feet away. Pardon me, it's 5 feet away, not 5.5, because this time we're looking just one level below the member GF. Then we're going to have the external reaction forces. Both are counterclockwise, all equals to 0. Solving for force HI, we get our solution as 25.6, pardon me, 7 OK positive. And this number is in compression. Now we can sum the forces in the x direction to find our solution for force EI. We're going to have horizontal component of HI. Then we're going to have the horizontal component of FED. And finally, the horizontal component of EI. All equals to 0. Solving for EI, we get our solution as negative 0.566K. Negative means, again, vector direction is wrong. Switching it over tells us that this member is in compression. Now we can use method of joints to find our required force in member ID. So let's draw the free body diagram of joint I. So we're going to have force IJ. Then we have force HI. Our force EI. And finally our unknown force ID. and the angle between ij and ei is going to be our phi using the geometry, and we can rotate our y-axis by theta in order to align it with our forces hi and ij. This would means that our x-axis will be rotated, and I'm doing it so that our equilibrium equation doesn't get too big. Now that we have done that, let's sum the forces in x direction in order to find our solution for member ID. So we're going to have horizontal component of member ID, which is simply cos our angle theta, which is 7.13 degrees, times our force ID. And then in the negative direction, horizontal component of force EI. Solving for ID, we get our solution as 0.416 K positive. This tells us that this member is in tension.